Hi and welcome to yet another video for my Year 10 GCSE Electronics students, and we're continuing looking through the mock exam paper. We're going to look at question 4, which the class average was only 40%, so this one was a little bit more tricky than the previous questions. So let's arrange a page. By the way, the reason why I've got two sheets here is because I completed a video for this very question. And I don't know what went wrong with the video. It didn't seem to fully record, so I'm having yet another go. So anyway, I'm getting some practice, aren't I? Right, let's have a look at the question. In fact, what I'm going to do, I'm just going to get rid of myself for the moment so we can just concentrate on the paper. So we're looking, first of all, let's just look at this circuit, and it's a very simple circuit in some respects. There's only two resistors, but they are of a particular type. This one is temperature dependent, and so it's a thermistor. So as temperature changes, its resistance changes. And this one is a variable resistor. So there's going to be a dial or a knob to turn. It doesn't have to be like that. It can be linear where you move something, but typically it's a dial. And and it changes the resistance. Okay, so these two resistors are arranged as a potential divider. So we're going to divide this voltage. Note that there we start with 9 volts and we drop down to 0 volts, and then so we're going to be dropping part of that voltage here, and then the remainder here. Okay, the proportion of the drops in voltage will be proportional to the resistances as well, and we'll come back to that in a little bit, okay, because to understand that is quite important. Let me just see if I can get a little bit closer. I think that might be helpful. There we go. I hope that's clearer. Now let's have a look at this characteristic curve. You do need to make sure that you understand these. Sometimes they can be a little bit intimidating students, but they're really important. So if you see, as temperature increases, so we're going up high, like you start at 0 degrees C, and then you get higher, 20, 46, and it goes up to 100 like this. And as you're increasing, the resistance on this vertical axis is decreasing. So when one quantity gets bigger, the other one gets smaller. Okay, or when the temperature goes to a lower temperature, then we increase in resistance. It's important to understand that, and there's actually what we call a negative temperature coefficient here. So strictly speaking, this thermistor should have -T, which tells us explicitly that this is a negative temperature coefficient thermistor, in that when one quantity gets bigger, the other one gets smaller. Now, so we've got a potential divider here, and so we're going to drop some voltage and then drop some voltage to get to 0 volts. Now, why does that actually take place? Let's just have a quick look and at hopefully a formula that you're familiar with. So we say that the source voltage in a circuit, in a series circuit, will equal the sum of the voltage drops. So V1 plus V2 plus however many things you've got in a circuit. So for example, let me just grab some blank paper. If I've got a battery, doesn't have to be a battery, but let's say it's a battery, and I've got a resistor here, and I've got another one here, and maybe another one here. Could even have another one here, as many as you like. Okay, each one of these resistors is going to drop a proportion of the voltage. So if, for example, this is a 9-volt battery, it doesn't have to be, but so we would say that one is 9 volts with respect to this side. So in other words, we've got 9 volts difference from one side of the battery to the other. Then you'll start at 9 volts here, and then you're going to drop to something, and then you're going to drop to something else, and then you're going to drop to something else, and then you get to 0 volts. So the sum of those voltage drops, so there will be a voltage drop there. Let's call that V1. And then we'll have voltage 2 drop, and then voltage 3 drop, like that. Okay, so progressively, as it goes around the circuit, the voltage is going to drop until it gets to 0 volts. So the sum of those drops. Okay, now if each one of these resistors were an equal resistance value, then each of the voltage drops will also be equal. And the reason for that is that the same current is going to flow around the circuit, the same current going all the way around. So we don't have to say like I1, I2, I3. It's the same current that flows through. It's a little bit like water being pumped around with the battery being the pump. So the same current is flowing around, but each one of these could potentially have like a different resistance, and so it will have a different voltage drop. The reason for that, if you remember, I like to say happy chicken, make it a little bit of fun. Okay, so make it like this. Okay, so we've got our little chicken here, and so we've got V and I and R. If I cover over V, you'll see that V equals IR. So this voltage will be equal to IR. Let's call it IR1 if that's resistor 1. And then this voltage drop will be equal to the current times R2, and then R3, and then this one is going to be IR4. Okay, so hopefully that makes some sense to you. And you'll note that each one of these has the same I, the same current flowing around. So what we could say is that the voltage drops are going to be proportional to the resistances. Okay, so for example, if this one has a resistance that's twice as big as this one, then the voltage drop across it will be twice as big, because remember, you're multiplying the resistance times the current to equal voltage. So that concept is really important to understand. Now let's just go back to this then, and hopefully this is making some sense to you. I know I'm going through it a little bit more slowly than I might need to for some people, but once again, Mark wasn't so good across the board, so it might help if we go through this one slowly. So like I say, there's going to be a voltage drop here. There's also going to be a voltage drop here. This voltage drop is going to be proportional to this resistance, going to be proportional to that resistance. Let's answer this first question. State the resistance of the thermistor at 0 degrees C. So if we look along here, we see 0 degrees C. And so then we go up, and hopefully you can see that should be fairly easy to see that that is at 25,000 ohms, which you could write 25,000, or you could just write 25k or 25 kilo ohms, like so. All right. Anyway, is going to be okay for you, but do make sure that you put units. Don't just write 25, because that could be whatever, 25 of something, but not stated. So you've got to state the units. Now the variable resistor is set to a resistance of 5 kilo ohms or 5,000 ohms. Variable resistor, it's this thing down here. So let's have that there. Okay, 5k. And calculate V out at 0 degrees C. Well, we set at 0 degrees C that the thermistor will be 25k. Okay. Now, so hopefully you can see that, going back to what I was talking about earlier, that voltage drops are going to be proportional to the resistances. That if this resistance is 5 times bigger than this one, because 5 times 5 is 25, so if this one is 25, then presumably this voltage drop is going to be 5 times bigger than this voltage drop here. Which is useful to know. It's not necessarily going to give you the answer straight away, but we can use the formula for that. So let's just grab the data sheet, which is inside the exam paper, and hopefully you'll be familiar with this one, which is the potential divider formula. It's saying we can calculate V out. It's going to be equal to the bottom resistor R2 over R1 plus R2 times V in. Now sometimes you might see it slightly different to that, because sometimes I like to, for whatever reason, I quite like to write it as V out equals Vs times R2 over R1 plus R2, and that's exactly the same formula, just written in a slightly different fashion. But whichever one you use, make sure that you state it. Okay, so I will state it as they have in the formula sheet. So I'm going to say V out equals R2 over R1 plus R2. Multiply that by I think they called it V in. Okay, it's the same thing there. Both of these are equivalent. Now, what do we know? Well, we know R2. R2 is this bottom one. It's always that way. Okay, so we've got R1 and R2. So we know R2, that's 5k. We know R1, 25k. R2 we know, yeah, that's 5k, and we know V in, which is 9 volts, that's the voltage, and then we can then calculate V out. So let's do that. So R2, now because these are, all of these are all K, I'm going to just not bother to write the K's in. So R2 is just, I can just write it as 5, and then R1 is 25, and then R2 again is 5, and we're going to multiply that by 9 volts. Let me just make a little bit more room on the screen. So if you do this, so what are we going to have? We're going to have 945 over, now of course you can use your calculator if you want, over 30, so what's that? That is 1.5, so 1.5 volts. That is the answer. Okay, now let's just have a quick sort of check. Does that seem about right? Well, first of all, 1.5 volts is less than the supply voltage. If you come out with like a value here, like 12 volts or something, that should be like an indicator to you that something's going wrong, because you only start off with 9 volts. So, and then also that is less. Seems like that's going to be about right, because we said that this is going to be a smaller voltage drop because we've got smaller resistance. This one's going to be bigger, and we also said this one's going to be 5 times bigger than this one. So if that's 5 times bigger, that would, so 1.5 times 5 is 7.5. So that would actually mean that this top bit, well, let's just write this in, 1.5 volts, and this would be 7.5. 7.5 volts plus 1.5 is 9 volts. So that is like a check, and that seems like that should be right for us. Okay, always worthwhile if you've got time, and many students do. If you've got time, do check your answers. Okay. Now, the next bit then, what happens to V out when the temperature increases? Causes a few people a problem. You've just got to think through it logically now. As the temperature increases, that way, okay, the resistance is going to now decrease, because we're going along and we're going down, 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 down. Okay, the resistance of the thermistor will decrease. So what was, say, 25k might then become 20k, and 15 and 10, and maybe it was 1k, I don't know, but it's going down, 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 down. Okay, now you've still got to drop the full 9 volts. So as this resistance is reducing, so too is the voltage drop across it. Therefore, that remaining voltage has to be dropped across this one, because remember, the sum of these voltage drops will equal the input or the supply voltage. So as you're reducing the resistance here, you're also reducing this, so this value has to increase. So V out increases. That's your answer. Hopefully that's okay. Now the next one then, I think the next one caused a lot of problems, okay, an enormous number of problems for people, because, and most of you did the right thing, you weren't too sure how to do it, so you stated the potential divider formula, because there's nothing wrong with doing that, okay. However, stating the potential divider formula is not, and maybe rearranging it and doing something with it, is not the easiest way to solve this problem. So we'll have a go at solving it a different way. But first of all, I think we should redraw this part of the circuit. So 40 degrees C, V out needs to be 5.4 volts. So we're gonna draw this circuit now. It's still a 9 volt supply or input, and we've still got the thermistor, the negative temperature coefficient thermistor at the top, and we've got a variable resistor at the bottom. Okay, so that's R1, that's R2, and let's just join that up, save confusion. And we're going to have V out. V out, it says, is 5.4 volts, so that's 5.4 volts above the 0 volts. Okay, when you measure voltage, it's always with respect between two places. Potential difference, it's also called. So what else do we know? At 40 degrees C. Now, if we know a temperature, then we should be able to look at the graph and find out the resistance of this top resistor. So let's do that. So 40 degrees C, and this is where it gets a little bit tricky, because if you look at that, it's a bit difficult to know exactly where it lies, but I would say that that is approximately 6K. That's what I would say. Okay, so 6K. So I'm just going to make a note there. That's 6 kilo ohms. Okay, and it's quite useful to add that note, because then, you know, if say you wrote 7 and the person marking your paper didn't understand where you got the 7, then, you know, if you're stating where you got it from, then that makes a lot more sense, and also annotating the graph that we saw earlier. So that's now top one, 6K, and determine the resistance of this variable resistor. So we don't know that resistance. That's the problem. We need to know that one. So if you write out the potential divider formula, it's not going to be an easy solution to you, and the reason for that is because you want to know R2, but you're going to have R2 here, and you're going to have R2 here as an unknown value. Now, it might be that you'll be able to solve it like that, but there is an easier way to do it. If you remember, I said that the sum of the voltage drops, all of these voltage drops around the circuit will equal the supply voltage, Vs or Vin. That if all of these add up to this, if we know the input voltage and we know this voltage drop, then we should be able to calculate that voltage drop. So the voltage drop across R1 is going to be equal to the supply voltage minus the voltage drop across R2. Voltage drop across R2. Okay, so let's do 9 minus 5.4. Okay, and that gives us 3.6 volts. It's very nice if you explain how you're doing it rather than just come up with a number. Okay, but you know, if you did magically come up with 3.6, I think we can assume we understand how you've got that. So we've now got 2 voltage drops in the circuit, and hopefully, if you were listening earlier, you'll understand that the voltage drops are always going to be in proportion to the resistances as well. So now that we know the voltage drops out and we can work out the proportion here, then it should be then possible to work out this resistance here. Okay, so we need to know, like, how many times bigger this is than this, and then we know how many times bigger this resistance is than this one. So let's do that. So 5.4 over 3.6, and if you do that, that's going to be 1.5 times. Okay, so what I'm saying is this is 1.5 times greater. 5.4 is 1.5 times greater than 3.6, which means also that this is going to be 1.5 times greater. So whatever this is going to be 1.5 times or 1.5 times greater than 6. Well, 1.5 times 6 is not too difficult to work out. So 1.5 times 6K is going to be 9K. So that's your answer, 9K. 9 kilo ohms. Okay, I was just about to write K, but I noticed that we've got that kilo ohms in there already. It would be worthwhile at this point just double checking that you've got the right answer. So first of all, if this is 9K, so if that is 9K and that's 6K, then I expect this voltage drop across here to be bigger than this one. Is it? Well, yes it is. Okay, so that's the first, just check whether it seems like a sensible thing that you've done. If you want to, if you've got time, you can then do the calculation. V out is going to be R2 over R1 plus R2, and then multiply that by V in. And then so let's just do that. So R2, which we said is 9K, and then over the 6 plus the 9, multiply that by the 9. Okay, and then if you do that, then you'll find that V out, if you do it on the calculator if you want, might be worthwhile just showing students, because some of you are not familiar with that, and it depends. I know that a lot of you are brain boxes with the maths and using the calculator, or even not using the calculator, but doesn't hurt. You are allowed to use calculators. Let's just do this as a fraction. 9 over you do 6 plus 9. I mean, I'm sure you can do 6 plus 9 is 15 anyway, but and then multiply that by 9. Okay, and then 5.4. So 5.4. So that's just our check that yes, that is those values, those resistances will give us an output of 5.4, which is what we were originally told we would have. Right, the next bit. The temperature sensor is now connected to a MOSFET. So this temperature sensor, this part here, this output is going to be connected to a MOSFET. When the temperature is 40 degrees C, there, so when this temperature is 40 degrees C, this output is going to be 5.4 volts. A fan is switched on, which produces cool air. The fan draws a current of 3 amps. Determine the minimum value of, now this G sub M is called the mutual transfer conductance. You don't need to memorize that for the exam, but it's handy to know where the M comes from. So what are we going to do? We're going to calculate that. Now you need to look for the formula. If you don't already know it, you need to look for the formula and you'll see that it's this one, G sub M, and the drain current. And that's going to, if that's not clear to you when we draw the circuit, maybe it will become clearer. The drain current is going to be equal to the mutual transfer conductance G sub M, and then bracket VGS, the potential difference between the gate and source pins of the MOSFET, or the voltage between the gate and source, minus 3. So let's just, first of all, if you don't know anything else, but you found the formula, write the formula out, because you often get a mark just for writing the formula. So the drain current is going to be equal to G sub M VGS minus 3. Okay, so we know that. That's going to typically get you a mark. And then, so the drain current is 3 amps. So we're going to write this bit here. Okay, that's 3 equals. We want to calculate G sub M. We want to find that. So we don't know that at the moment, G sub M. The voltage between the gate and the source is the input voltage. It's this 5.4. So, and that will become a little bit more apparent when we draw the circuit out. So that's 5.4 minus 3. Then we need to rearrange that so we've got G sub M on its own. So we're going to do that. So what do I need to do? I need to get rid of that. So I'm going to divide this whole side by this, and then I've got to obviously divide that side by the same thing. So that's what I'm going to do. So I'm going to say that G sub M is going to be equal to 3 divided by 5.4 minus 3. Now, of course, if you want to at this stage, you could have subtracted 3 from the 5.4, so 2.4. But it's yeah, whatever. Okay, 1.25 if I'm not mistaken. But if you want to see that on the calculator, we are going to have 3 over and then 2.4, which is 1.251 1/4. Okay. 1.25 Siemens. Okay. Last bit. Okay, complete the circuit diagram to show the final design of the cooling system. Now remember, it's going to turn a fan on, and we're using a MOSFET. And I did mention to students, and it's, I can't really stress enough to you guys when I tell you you're going to have to memorize the drawing, the symbols for a MOSFET. You absolutely have to memorize it. And it's not just GCSE students. A-level students typically find it quite problematic drawing a MOSFET until I tell them, you've got to memorize it because it's going to come up. Same with other components, like NPN transistors, thermistors, thyristors, xenodiodes. You need to memorize them. It's all very well being able to use it in Circuit Wizard, but you have to memorize the component symbol and know how to use the symbol as well. All right, okay, so let's just draw the MOSFET. Now MOSFET has a very high input impedance. Think of impedance as resistance into the gate. That's the gate. Okay. Now notice where I drew it. It's like an L there, and then we've got 3 lines, and then the middle one's got an arrow facing in, and then we've got these lines like this. Okay, it's important that the arrow faces in. That's the particular type of MOSFET that you'll learn about at GCSE level. Don't worry about any others. But you do need to draw the arrow in. It needs to be the correct symbol, okay? And I'm going to write an M in a circle, and that just means that's a motor, because we don't actually have a symbol for a fan, or maybe there is, but it's quite acceptable just to write M for motor. We don't need a resistor here because it's got a very high input impedance or high resistance, so there will be no flow of current that way, okay, or next to no flow. There's something called a transitory flow or temporary flow, just as it's charging up. Even the gate has a capacitance, but don't worry about that, certainly not at GCSE level. That's the gate terminal, that's the drain terminal, and that's the source down there. And so when we're talking about the drain current, we're talking about the current that's flowing into or down the drain, I suppose you could say. Okay, hopefully that's fairly clear. Now, complete the circuit diagram. They only give 2 marks, and I think all they're expecting here is the motor to be above the drain, between the source voltage and the drain, and then also a MOSFET and the connection to the gate. Ideally, if you were actually building this circuit, because a motor is what we call an inductive load, so anything like a solenoid, a motor, anything with an electromagnetic field, you want to have a freewheeling diode, which is going to be like this. It's in what we call reverse bias, so current can't flow like down it, okay? It can only flow that way. At GCSE level, just accept that you need one of those, unless you've got something like a heater or a light bulb, which doesn't have a coil which stores electromagnetic energy. Don't worry about the details of why that's needed, just have one, okay? So that's going to get you everything that you need. I think, just complete the circuit diagram, and I think that's it for this question. Yes, it is. So hopefully this video is recorded properly this time, and I will be uploading it, and I do hope that you find these useful. I've created feedback sheets for every student, individualized feedback sheet, which tells you your score on each one of the questions, and then hope that you're using these videos to catch up with, like missing bits of knowledge and practice these things, because electronics is fairly predictable, or the exam is fairly predictable at GCSE level. So if you didn't score like a really good score on each one of the questions, with practice you should be able to, and in the future there's likely to be very similar questions too. Okay, thanks very much for watching, and look out for the next one.